All right. So start here. Before you get going, I showed you guys this kind of tool, I believe, on Friday, kind of that figure out your grade tool. Any questions over that? So I should be getting those iClicker scores updated with your 3 lowest drop. Hopefully this afternoon. If not, definitely tomorrow they'll get up there, posted up there on Canvas. And then you have those 3 assignments kind of sitting there due at the end of the week. Once again, you can kind of pick and choose a little bit of those Excels. If you've done the first 4, right, you don't do one, or if you've done the first 3, and you don't do one of them, that will be a 0. That will be the one that gets dropped. So I've dropped the lowest of each type, right? 1 Connect, 1 Excel, whatever your lowest score is. Those obviously won't be reflected kind of in the grades until past those due dates. So on Monday, by Monday, I will have kind of those Canvas grades updated to reflect kind of your lowest Connect and your lowest Excel drop. Okay. And then you should have like a very clear idea of where you're at going into that fine. Okay. Any questions before you jump into today? So I've also got those practice exams up there. Start taking a little bit more look at those, probably maybe even starting Friday. But definitely kind of we'll do kind of a review class next Monday of finals week. And I forgot to pull up this specific sections, but I believe I want to say we have a Thursday exam, but I mix up my classes sometimes. So let's double check. Yeah, so Thursday at 9:45. Okay. Also, I know a lot of people aren't aware of this. If you just, well, here I'll go back. If you Google search Ball State final exam schedule, I don't just like pick these times out of Blue Air. There's an actual kind of method to the university's madness. So if you're not sure about a class, you can't find a final, I don't know, about the professor, you can use this and then you just look for like your class. So for instance, okay, I've got a 3 credit hour course. I'm taking it Monday, Wednesday, Friday. It starts at 11. Thursday at 9:45 is the final exam time slot, right? So you can figure out whatever slot, if you do it before, I think, I don't know, gave you the exam early and you'll get on Monday or something in class, that's different. But if they actually use the final exam 2-hour time slot, this is the schedule of how you can figure out what that is. Okay. Any questions for me before we dive into material here today? So this week we will pretty much be just going over a lot more linear regression examples. So I'm going to be going through really the same things over and over. Just in the context of different examples. So I'll mention things we've already talked about. But really we have all of like the basics or the principles down behind what you're going to be going to that final. It's just getting more practice with them. Okay. So we left off last class. We were looking at these examples where we said, okay, what's the impact of basketball expenditures on whether or not that team makes a tournament, right? That program success. Then kind of left it off at the end, said, okay, that doesn't seem that important, but is getting this national exposure in the tournament, does that have some type of impact on the academics of that university the following year? So what we're going to first take a look at is, okay, this huge national exposure, right? From making the tournament in the prior kind of academic year, well, that following fall, right, that following year, what's the impact that making that tournament has? Right, this is just a 1-0 variable. 1 if you made the tournament, 0 if not. What's the impact that has on applications, right? Or what's the predicted increase or decrease that has in the number of applications? Now, going into it, we probably already could guess, like, there's probably a positive effect, like having more national media exposure probably isn't a bad thing for like getting people to look at your university. And so we can run this very naive regression, right? So here, the way we interpret that slope coefficient or our slope estimate, we've got whether or not the team producing a tournament. So going from the 0 to the 1 group is our 1 unit change. So going from not making the tournament to making the tournament in the previous year, we would expect that application to go up by about 7,000. We'll talk about why this is a little suspect in a second, but for right now, all we're thinking about is, okay, so if I wanted to predict the number of applications just from whether or not they made the tournament or not controlling for any other factors, my intercept or my constant coefficient is what, 7,444? I then have my slope coefficient on previously making the tournament is 7,337. So if I wanted to predict the number of applications for a team, like in spell, that previously made the tournament, well, that would mean that this is a one variable, right? So kind of my predicted applications here would be times 1, which is really just the intercept plus the slope, right? So it's like the additional impact of belonging to that one group. Because if I wanted to make predictions for all the teams that didn't previously, or all the teams, yes, didn't previously make the tournament, well, now when I look at that coefficient, it gets multiplied by 0. 0 doesn't change anything. Notice here for a team that didn't make the tournament, well, that's just the intercept, right? That's kind of like wherever university starts, and then if you make the tournament, here's the additional kind of bump that you would get in your predicted number of applications the following year. Okay. So once we have those coefficients, we can start to make predictions. Here, these are very easy, basic predictions, a very naive regression. In fact, I mean, do you really think that the number of additional applications from previously making a tournament would be an additional 7,000? I mean, that's pretty large, right? So what's probably going on here? Well, teams that previously make the tournament, or teams that in the previous year were more likely to make the tournament, probably larger universities, right? Teams that belong to big conference we see show up kind of in the a lot more. So having a higher student, total number of enrolled undergraduates, having all these other factors that would increase applications in previous years might be correlated with whether or not they made the tournament. So we're not just picking up the effect of previously making the tournament, we're also capturing the effect of having a larger student body, the effect of having higher revenues coming in outside of the athletic department, right? Maybe alumni donors and things like that. So I want to start to control for those things. As I can control for additional things, I'm eliminating a lot of that bias that exists in that coefficient. We said, let's be cautious. These are still just evidence of a correlation. It's not causal. Now, as we include more controls, we're getting closer to that causal relationship. But if we're doing a very naive regression with just one X variable, we're having a lot of bias probably because there's a lot of other things that matter that we're not including. In fact, one of the statistics we talked about that predicted whether or not, that told us about how reliable our estimates were is this R squared. Does anybody remember kind of just like a base, it doesn't have to be the most technical interpretation of what the R squared represents?
How much it can actually predict.
Yeah, it's some measure of like how accurate our predictions are, or be a little more technical. The amount of variation in our Y variable, so the amount of variation in applications, we're explaining with our predictor variables or our right-hand side X variables. Right? So here, whether or not you made a tournament, it's only going to explain a proportion of 0.07, right? Or 7%. There's still 93% of the variation in predicting applications that we can't explain. That's a pretty large amount, right? So we'd probably be pretty cautious if like using these results to make policy implications or to suggest things. Right? So we might want to include some additional controls. So one thing that you'll see done a lot, because I was mentioning things like, well, there's all these other factors in the previous year that would have been correlated with having more applications, just having a larger university, that are also going to make it so that you're more likely to make a tournament. So what's one really good control I could use if I have data on it? What's the number of applications I got the previous year? That should be a really good predictor of how many I'm going to get the following year. Right? So this is a pretty strong control. Anytime you looked at this is what we call kind of a lagged variable. So it's looking at your dependent variable and looking at what was it last year. Right? So now the interpretation becomes a lot more important, a lot more powerful. I'll use that word. Right? So now the interpretation of that coefficient on our previous tournament variable, do they make the tournament or not? It's holding constant the number of applications they got the previous year. So two universities, previous year got the same number of applications, but one of them goes from the 0 to the 1 group, right? Sees that 1 unit change. So goes from not making to making a tournament. Now we expect their applications to go up by about 100. That seems maybe a little more plausible, right? They do get a slight increase in the number of applications, but that's holding constant now the previous year's applications. That's a lot more powerful of a statement. And we've eliminated a huge bias in our coefficient, right? Went from 7,000 to 100. That means that, yeah, the number of applications I was getting the previous year influenced by all these other factors. We're also probably making it more likely I'm going to turn, right? So it's going to kind of pick up that bias point. Once you include it as a control variable, right hand side x variable, we now eliminate that bias. Okay. Questions on that idea? Yeah. Yeah, if I asked you about, why are we seeing a difference in this coefficient? I mean, probably won't ask you a question like that. If you look at some of the regression examples on the practice exams, probably wouldn't do something like that. But I would give you this output. I'm not making you run these regressions in Excel or anything on the exam. I'll give you the Excel, or here, this is a slightly different version than Excel, but we'll get a lot of Excel examples this week as well. And it's the same structure, right? It just looks a little bit different in terms of like font. But yeah, I'll give you this and then maybe ask you questions like, interpret that previous tournament slope coefficient, or interpret the number of previous applications. So if I was trying to interpret the coefficient on the previous year's applications, what would that be? So the general interpretation you said is always a 1 unit change in our x variable causes the predicted y variable to go up or down by, I think if it's positive or negative, whatever that coefficient estimate is. So here, what's a 1 unit change in previous applications? How would I measure applications? Just number of applications. So what's 1 unit increase? One more application the previous year would predict that this year's applications go up by 1.03. Now, when we say goes up by, right, that would mean, yeah, if I got every additional application I got the following year, I can basically expect to get that same number the next year, right? I can get another one the following year, plus a little bit more, right? And this probably is just picking up that, and this is a little bit older data, so it's probably picking up like just the trend that like more people are attending universities, right? But it's controlling for that now. It's saying, okay, going for the previous year's applications, now what's the impact of whether or not I get turned in the previous year as well? So we can interpret these different slope coefficients. That might be something I asked you. I could ask you to calculate the test statistics. I probably will. I'm trying to give you easy points there. Remember I said last class, or it might have been even Wednesday, how do we find these test statistics? You simply take that estimate for the slope, you divide it by the standard error. So I'm giving you them, the output gives them to you here, but how am I getting that test statistic? Taking that coefficient of 101, dividing by that standard error of 67. All I'm doing is that coefficient, or sorry, get that test statistic, right? You simply divide the coefficient related to that variable by the standard error that's related to that variable. Questions on that? Okay, so if I'm looking at that previous applications variable, what levels can I say that I can reject the null at? So remember, what do we always start out assuming about these slopes? Whoops, we always start out assuming that they're zero, that there is no relationship, right? That as x changes, well, x times 0 would be 0. So we're assuming there's no relationship between this x and y variable, that x cannot predict y at all, right? So if we see a p-value associated with our coefficient estimate that's less than alpha, well, we can reject that null. Well, if I'm rejecting that there's no relationship, I'm saying I found evidence there is. Right? So the levels that we can reject the null at are the same levels we can say we found that there is a significant relationship, which is why we use, that terminology of significance, right? So I said you can go back and forth, right? 90, 95, 99% confidence, 10, 5, 1% significance. We use the kind of significance levels usually with, regression, because we're saying there is a significant relationship at these levels, right? Or we're rejecting that there's no relationship at these levels. So here, if I've got a p-value of 0, which levels can I say there is a significant relationship or reject the null at? Oh, yeah, my p-value is 0. I should be able to reject it everything. Right. Now, very, very significant relationship between how many applications I get the previous year and this year. That makes a lot of sense, right? Now, what about whether or not I made a tournament the previous year? Well, there I've got a p-value of what? Yeah, all I do is go to that coefficient estimate for previous tournament. Go over to my p-value column, 0.135. So what levels can I reject the null at here, or say that there's a significant relationship between previously making the tournament and the number of applications the following year? None of them. 0.135 isn't going to be less than any of those alpha values. Right? So making our rejection decisions, it's as simple as we're going to be given that p-value. You're not going to have to look it up when it comes to linear regression. You're going to have that from Excel or some other data programs kind of output, right? All you have to do is compare it to alpha. If it's less than alpha, you can reject that null, that there's no relationship, or say you found evidence that there is a significant relationship. Okay. Any questions on that idea before we keep moving? Okay, shouldn't be too bad. Now notice, once we include the previous year's applications, what happened to our R squared? Went way up, right? The proportion of variation we can now explain is 0.97, or we're explaining 97%. So this kind of highlights like these lag terms. Like if I know the number of applications the previous year, that's capturing a lot of the characteristics about the university just in that variable, right? Anything that would predict applications the previous year, captured there. So we're a lot more confident with these results because there's only like 3% we can't explain, right? The proportion we can't explain is like just under 0.03. Any other questions on this before we keep moving here? So another thing we can kind of do, just to kind of highlight, I don't know, the importance of additional controls, is I could also include, and I think I said a little bit about this last class, but like these things called fixed effects. So this is the idea that I'm just going to include indicators for every single state. So like state 2, I don't remember how it's somewhat alphabetical, but so that'd be like, I don't know, Alabama. It was a 1 if the university was from Alabama, 0 if not. State 3, 1 if it was from Arkansas, 0 if not. So on and so forth. So if I include indicators for every single state, what I'm now saying is holding constant everything else in the regression. Here's the expected kind of increase in applications from previously making the tournament compared to not. And that's more powerful because I'm saying 2 universities with the same number of previous applications, but they're in the same state. Well, we know that demand for, doing a California public, universities versus Delaware, right? There's vast differences in just the number of people who are applying. And so we're now controlling for what state that university is in. Now, if one of them makes a tournament, we see the expected increase is about 167 applications, and our p-value is 0.017. So we now can say that there is a significant relationship between previously making the tournament and the number of applications. At what levels? When we say at the 10% significance level, 0.01 is less than 0.1, so yes. What about the 5%? 0.017 is less than 0.01, so yes. What about the 1% significance level? Not quite, right? It's just barely above, well, I shouldn't say barely, but 0.017 is not less than 0.01, right? So we failed to reject the null there, or can't say that we found evidence of a significant relationship. Any other questions on this example before we kind of switch? Well, not completely switch gears, but. Okay. So just I'll go through these kind of quick because I don't want to hammer this too much, and I think the other examples will be more useful today. But I basically did a kind of similar thing where it's okay. Instead of the number of applications, well, I've erased everything now. So let's say 75th percentile of the ACT math score of the incoming freshman class. And I kind of did a similar thing. And really what we're going to kind of focus on, we could also say is, okay, what was the effect of that previously making the tournament variable? And I've just controlled for the number of previous applications here as well. I didn't have a ton of additional controls in this variable, or sorry, in this data set. So now what would the interpretation be? Well, Our previous tournament variable is still 0, 1. So going from a 1 unit change, just a 0 to the 1 group, going from not making the tournament to making the tournament, we would expect that the incoming freshman classes ACT score, the 750, kind of think about this as the average, if that seems easier, would increase by about 1.5 points. So it's kind of this significant impact that having that success in the tournament was leading to being able to have a higher academic quality incoming freshman class the following year. And this is maybe suggests, like if I saw that there was a positive effect on applications, and then I see, well, there's a positive effect on the overall kind of average academic quality, what that's really kind of suggesting is that with these additional applications, maybe I wasn't just admitting more students, but I was being more selective, right? Maybe I admitted the same number of students, I just chose more of them from the right-hand side of that ACT score distribution. And p-values here of basically 0, right? So we could say that it's, high levels of significance here, right? Or high levels of confidence. Questions? Yeah.
So you know that like
Yeah. Yeah, right. So that's the next step. So we can interpret these coefficients, figure out if we found evidence there's a significant relationship. We then say, okay, how confident are we in this? We look at the R squared. Well, here, when it came to the incoming freshman classes like ACT scores, I'm only getting about, or explaining about a proportion of 0.28 of the variation in that incoming freshman classes ACT math scores here. I'm not explaining like 70-ish%, right? So I should probably be a little bit more suspect of these estimates than I would for my previous regression where I had an R squared of 0.97. Yep. Yeah, we want an R squared as close to 1 as we can possibly get. So what's one way I can get closer to an R squared of 1 here? If I had more data, I had more additional control variables to kind of throw those in. Maybe do the state, fixed effects thing here again, right? But I just kind of wanted to round out this example. You do the same thing for the English score, kind of find it very similar. It doesn't really change, it doesn't matter what subject I measure kind of academic quality in. We would see kind of a similar story. Once again, though, pretty low R squared, should be a little suspect. We'd like to, in this case, go out and try to get some additional data on these universities. All right. Any questions on these examples before we kind of switch up a little bit? Okay, so I'm gonna skip ahead. Where do I want to go? Yeah, I don't want to talk too much about this. I don't know if we'll have time for that. I don't know. Focus on that. We'll probably do that next class. Here we go. So, kind of thinking about these dummy variables that are just 0, 1. We call them dummy or indicator variables. I don't really know where the term dummy comes from. I think it has something to do with programming, is why we call it that. But let's think about, let's say I wanted to do predict income from the years of education, right? So I want to include not just like how many years of education someone got, because if I go from 10 to 11 years, I still don't have a high school degree. If I go from 11 to 12, assuming that not like failing, but like 11 to 12, then I should have a high school. Like there's discrete jumps, right? Having a high school degree, having some college, having a college bachelor's degree, having a graduate degree, right? There's different jumps in this education. So maybe instead of kind of making this nice continuous number of years of education, I want to create these different categories. Did somebody have a high school degree? Did somebody have did somebody have a college degree, right? I want to kind of capture all these different jumps in the education. So I'll include several different dummy variables, right? I can include several of those dummy variables on the right-hand side. Now, I can also include additional control variables, right? So maybe I want to control for, I don't know, the person's age. Maybe I want to control for the person's socioeconomic class, right? Their income level, right? But, or sorry, I couldn't do that. I'm looking at income here. Well, control for, I don't know, other things that we might think impact income, right? Like maybe the state that they're in, or all these other different factors. So what I'll start doing is, okay, look, the first dummy variable I include is, did they have a high school degree or not? The second one I'm going to include is, did they have any level of college, right? Have to have some level, like they didn't obtain a college degree, or at least they didn't obtain a bachelor's degree, but they had, some credit hours. Right? The next one will be, did I get a bachelor's degree? And then the last category I'll kind of think of, did they get a graduate or professional degree? Like, so master's, PhD, JD, MD, something like that, right? Now I could break these up into more categories, but just for the sake of this example and not get too many. Okay. Now, there's one group that I didn't really include here, right? So I've got people who have high school degrees, some college, bachelor's degree, or graduate degree or more. What could I have that I wouldn't belong to any of those groups? No high school degree, right? I dropped out in high school, right? So the reason why I had to leave one of those groups out, so I'm thinking about something like, skip ahead here, with education, right? Is I always have to, we said the interpretation is going from the 0 to the 1 group. If I also included a control for whether or not they had less than a high school degree, who's the 0 group? Who am I comparing to, right? You have to belong to one of these categories, right? And so I always have to, if I've got these multiple dummy variables, I've got to leave out one group to be my base comparison group. All right, so here I'm going to leave out less than a high school degree. So if I leave out less than a high school degree, my interpretation goes, okay, going from that 0, that base group, the group I left out, so not having a high school degree, to having a high school degree, here's the predicted change in my income. What do you think is probably true about the sign of this coefficient? It's positive. If you have a high school degree relative to not, positive impact on your predicted income. What about having a bachelor's degree, right? Relative to the group you left out, so relative to not having a high school degree, what do you think this coefficient sign probably is? Positive as well, right? Comparing to someone that has less than a high school degree, obtaining a bachelor's degree, you would predict higher income. What's probably true about the size of this coefficient relative to the size of the coefficient on having just a high school degree? Larger, right? The impact of having a bachelor's degree on income or predicted income, probably a greater increase than the predicted increase from just having a high school degree. In fact, what probably is true about these coefficients as I'm going from B1 to B4? Yeah, they're getting larger, right? I'm getting higher levels of education. What's the main point of that? I mean, we all want to be more enlightened, but like most people are obtaining higher levels of education because it opens doors to higher paying fields, right? Or higher paying pathways, right? So, we kind of, are able to then estimate this and say, okay, is that actually true, right? Do we see that these coefficients are growing in size if we had some actual data, right? Now, how did I know which one to leave out here? Typically, we're going to leave out either what we expect to be the lowest group or what we expect to be the highest group. If I don't have any clue, we just use our best judgment. Right? In fact, it's kind of a sneaky way we can actually choose. If we're not sure, which one do we leave out? So I'll give you another example to kind of highlight this. So let's say I've got athletic revenue data, right? And I know that varies wildly across universities, and it's really highly correlated with what conference are you in, right? You look at it, like the SEC relative to the MAC, right? There's very different levels of revenue generated by those schools, right? So I'm just going to do a very basic thing, which is, okay, how can I predict revenues, athletic department revenue, just from what conference a team belongs to? Now, obviously, there's going to be differences. It's going to be different for anyone, but on average, what's the expected increase or decrease in revenues from belonging to this conference? So each one of these is a dummy variable. 1, if that team belongs to the SEC, 0 if not. 1, they belong to the ACC, 0 if not. But I have to make sure I do what here? I need to leave some conference out. I'm going to leave the American Athletic Conference out, right? I don't even know what teams are in there, so I have to look it up. But I'm leaving out this conference. I didn't hear of them, so I'm thinking they probably have pretty low, right? I want to leave out either the highest or lowest. So I'm going to leave them out. I run this regression. How would I interpret these coefficients? Right? So it's going from that 0, that base group belonging to the American Athletic Conference, to then joining, like going to the 1 for that variable, so going from the American Athletic to the Sun Belt, would predict my athletic revenue goes down by about 25 million. What if I belong to the SEC compared to the base group, American Athletic Conference? Well, there I'd expect predicted revenues to be about 71 million higher. So this is really telling me that what's the best conference to belong here? If I look at these coefficients. SEC has the largest predicted increase in revenue. And I guess like, what's the best one? The best one in terms of revenue, right? We're just thinking about dollars here. What would be the worst conference to belong to? Yeah, the one with the largest negative coefficient, right? Or the Sun Belt. In fact, relative to being in the American, if I'm in the American Athletic Conference, what conferences do I not want to switch into? Any of these that have a negative coefficient, because that would mean my predicted revenues would fall. Or I guess I don't want to come in with any either. Other questions on that? Yeah.
So like when you ran that in Excel, would that cell be empty then?
Yeah, so think about it this way. You could have an indicator variable for every single conference. You just have to make sure you leave out one of those columns. Because you'll still have the data there, you just need to leave one out. In fact, it gets a little bit easier. I actually didn't choose the American Athletic Conference here. I don't know why, do you go to an example? What I did was I just ran it off to prove this, to show this to you or highlight this point to you. Notice I have the American Athletic Conference kind of cut off down here, and I just got zeros. Excuse me. So what Excel does, if you ever run it with these multiple dummy variables, it recognizes, oh, you have to belong to one of these. Like there's no observations where that all these are zero, so I need to drop one for you, right? You did something dumb, so let me fix it, is basically what Excel is saying. Now the problem is, I actually don't know how it picks and chooses which one it drops. I think it's a little bit random. Again, it has something to do with like the ordering of the column. But there's no real significant meaning to it. So if I'm looking at this and I want to run this regression again, what would if I had, you know, the American Athletic variable in there, which one would I want to leave out probably? Sunbelt, why? What would happen to all my coefficients if I left the Sunbelt out? They're my comparison group. They had the largest negative coefficient. Now they're my base group. Every coefficient is going to be positive. I could have also left out what other team would be maybe smart. SEC. If that's the case, all my coefficients become negative. Right? So leaving out the highest, leaving out the lowest, it's a lot easier to kind of like rank order whatever these dummy variables are. Okay?
Questions on this, and then, you know, some of these we can't say are significantly different, like some of the p-values are you know,
A little bit higher. But a lot of them, right? You can definitely say about the SEC. Anytime we see these e to the negative, we said these p-values are basically what? Zero, which means my p-value is definitely gonna be less than alpha. I can definitely reject that null, which is that there's no effect, right? Or said differently, I found evidence of a significant relationship.
Any other questions on this example before we keep moving? Okay. Let's skip ahead here to kind of give us this look. So
Kind of a similar idea where we have these multiple dummy variables. I had this data set, and I think it's described as a large southeast city in Texas, so I'm guessing it's Houston, but it's all this traffic stop data. And it has kind of what was the result of this traffic stop. So the two variables we'll look at, and we won't get to the one today, but we'll start looking at, okay, this 1, 0 variable for whether or not a ticket was issued. Okay. So once this traffic stop occurred, 1, if the officer ended up writing a ticket, 0 if not. I then include these other groups, right, for the different combination of officer driver rates. So I had a 1, 0 variable, which was a 1 if the officer was white and the driver was non-white. I had another one which was a 1, 0, 1 if the officer was non-white, driver was white. And then another 1, 0 variable where the officer and driver both non-white. So here my comparison group would be what? Which one did I leave out? What combination? Both officer and driver white, right? So all these coefficients will be relative to when the officer and driver were both white. What's the predicted change in my y variable when the officer's white and the driver's non-white? Now, we said last class, anytime I have a 1, 0 variable on my left-hand side for that y variable, my units, like with income, this was the predicted change in the number of dollars. But if I have a 1-0 variable on them predicting that dependent variable, we said the units are like, remember? So it would be like a change in the probability, right? Going from that 0 to the 1, right? So my units for a 1-0 dependent variable, it's gonna be like the predicted change in the probability, as opposed to like predicted change in dollars increase for income. Okay? So if I think there's discrimination going on, white officers, non-white drivers, what would I expect this coefficient to be? Positive. So if I see positive coefficients here, I'm like, got some discrimination going on in my police department, right? And we can hold constant other things as well, right? So we can hold constant. I got things like officers' years of service, driver's age. So I'll show you this data, and then we'll kind of look at the outcome here. And actually, let me go back to what this. I can't now. Well, I can remember what I did, I think. So this is what it starts out looking like. You download the data, okay? So I've got my Y variable here, which is whether or not it's a 1-0 variable for whether or not they got a ticket. I also have kind of my different kind of combinations of driver, officer being white, non-white, right? In fact, I don't think I quite have that here. We're gonna probably work on that next class, but for now, let's assume that's what those three variables are. I will kind of, I think these are only like, was the driver white, was the officer white, so we have to kind of do some like combinations to create those other three categories. I've also got things like the driver's age and officer's years of service. I want to include those as my control variables. Now, the problem is if I go to my data analysis tab, when I select my X variables or my right-hand side variables, I can't select them if they're not next to each other. Well, I can, but Excel won't run the regression, right? So one issue is if I want to include just the driver's age and the officer's years of service, I need to make sure that's right next to these racial identifiers that I have. So how can I do that? I just click on the column. I move this over, right? I click on officer's years of service. I move this over. Now, everything's right next to each other. These are the 5 independent X right-hand side variables I want to use. Here's my Y variable, right? Now notice, if I go to my data analysis tab, I go to regression, hit OK. My Y variable doesn't have to be next to my independent variables, right? Notice there's a column, this arrest column is separating them. That's okay. It's just that all your X variables have to be next to each other. So I select this ticket variable, Control Shift. If you don't have a control key on your Mac, hit Command Shift and the down arrow. Go to your X variables that you want to select. Excuse me. We're going to include those 3 racial kind of identifier groups, the combinations, driver's age, officer's years of service, Control Shift, Command Shift on a Mac. Make sure we have that labels button selected, hit OK, and it's going to give us that output. Okay. Like I said, we have a little bit more work to do to get what I'm about to show you because those variables weren't quite what we wanted, but we'll work on that next class. So let's assume I run that regression, right? I've got my 3 different kind of officer, driver, race combos, and then I just had driver's age and officer's years of service, right? So I look at these results. How would I interpret these? So when the officer is white and the driver is non-white, relative to when the officer and driver are both white, right? Going from that base comparison group 0 to the 1 group, the change in the predicted probability that a ticket is issued goes up by about 0.067 or approximately 7%. What's the bad news? Right? And it's holding constant the driver's age and the officer's years of service. Also, all 3 of these coefficients, we find all of them are positive. Right? Now, kind of an interesting thing here as well is that you think about relative to when the officer and driver are both white, when the officer is non-white and the driver is white, we also find an increase. So not only do we see racial discrimination potentially going on one direction, we see it kind of going both ways, right? And these p-values are basically what? E to the negative 75, 18, move the decimal that many places to the left, they're all 0. So really, we found that race is playing, sorry, I shouldn't just say race. The race combination of the officer driver is playing a huge role here. Now, I might want to be a little cautious of these results because what else do I have highlighted up there? The R squared. So we said that is the basically how good my predictions are, how much of that variation of my Y variable I can explain with my X variables. I'm explaining 3% or a proportion of 0.03. So there's still a lot of other things out there that matter, like probably a good control would be like whether or not there was a warrant out, that was like the reason of the traffic stop. What was the speed, right? Or what was the speed limit where they're at? So all these things that we're not controlling for, looks like there's a lot of other things that matter, right? 97% of the variation, we can't explain with just these variables. Right? But we can still interpret them. I guess it's still like a first stage. You might want to then try to go out and get more data so we could run a regression with more controls. Just thinking about doing some more of this interpretation though, how would I interpret my driver's age variable? So remember, it's a 1 unit change in my X variable, changes my predicted Y value by whatever that coefficient is. And because we have a 1, 0 Y variable, the change in the Y value is the units is like changing the probability. So what would my interpretation be there? What's a 1 unit change in driver's age? Yeah, 1 more year, right? We measure years or years. We measure age in years, right? So for every year older a driver gets, right, every 1 unit change in their age, we would predict the probability that a ticket is issued goes down, right? Not only goes down by 0.003, so if that's a probability, it goes down by 0.3%, but very significant, right? P-value is basically 0 here too, right? Excuse me. So what that's basically saying is like the older you get, the less likely when you get pulled over, you're gonna get a ticket. I don't know if that's just because you learn the right things to say when you get pulled over, or if the officer is viewing you as though you probably are a better driver, right? When you're young, you just do dumb things when you're driving anyways. And so that's kind of capturing that, right? Now, what if I want to say, okay, what's the effect of being 10 years older? Yeah, if I know the effect of 1 year, just scale it up, multiply that by 10, right? So if I'm 10 years older, that would be what? 0.03, so I'm reducing my chance of getting a ticket by about 3%. Questions on that? How would I interpret the officer's years of service version? Shouldn't be too bad, based on what you just said.
Or like maybe get to get more officers at that job.
So officers' years of service, we're measuring the officer that pulled them over, how many years do they have in the job? So what would a 1 unit change there be?
1 year.
Just having 1 more year on the job would change the predicted Y value, or here, it's a 1, 0 dependent variable. So a change in the probability that I go from the 0 to the 1 group would actually increase the probability I get a ticket, right, by what, 0.0027, so just under 3% again. Right? So this is the idea that if an officer is on the job longer, I don't know, maybe they're more accurate in identifying who really was breaking up. Maybe they're just becoming like old and curmudgeon-y, and they're just more likely to write tickets. I don't know exactly what's driving this effect. That's something we want to maybe dive into a little bit more. But we did find a very significant effect of officers' years of service on whether or not they issued a ticket. Right? Questions on if you get pulled over, I guess according to this, right? We would hope like you see somebody who looks like they're fresh out of the academy, you're like, that's a lot better, right? Because if you see someone who looks like they're 50 or 60, that's going to take the effective 1 year of actual service, multiply it by 20 or 30, right? You're much more likely to get a ticket from that. Now, again, cautious of making statements like that. That's the correlation we found. Still a lot left that we can explain. It's probably not the end all be all. We want to kind of go out and gather additional information, additional data that we can have additional controls on the right hand side there. Questions?
This is like so one thing I'll point out here, as we're kind of ending. So if I got 22,000 observations, we could go back to show you the standard error. So we said this is how we find the test statistic, right? So just like before, like if we had sample means, remember like this denominator is kind of representing like the variance in that coefficient. So before when we were doing variance, we had things like that looked like this. So when our sample size went up, it kind of decreased our standard error. This decreases, or I shouldn't have said variance here, sorry, standard deviation. It decreases the standard deviation, our test statistic goes up. Our test statistic goes up. Right, our p-value is kind of getting smaller and smaller. So when we have really high sample sizes, same principles apply. We want a lot of data when we run these regressions, because when I have really high sample sizes, like 22,000, guess what happens to a lot of my p-values? Well, if my test statistics are getting larger, my p-values are getting smaller, it's going to be more likely I can say that there's a relationship between these x and whatever y variable. So same kind of principles apply that we were doing with one population hypothesis testing. Higher sample sizes always make it more likely we can reject the null. In this scenario, more likely we can reject that there's no relationship, or say we found evidence that there is a relationship. Okay. Any questions on that before we get out of here? So we'll keep on working on regression stuff on Wednesday. I'll just bring in a few more examples. We'll kind of take a look at a different dependent variable, which is not did you get a ticket, but did you get arrested? Right? And kind of see, can we find evidence of any discrimination going on there? If you have any questions on any of those homeworks, feel free to reach out. Please work on them early in the week. I will not be that available on Friday. So if you have last day questions, I can't promise they're going to get answered on Friday. Okay. So get me those questions early in the week. Other than that, I'll see you guys on Wednesday.